The asteroid that killed the dinosaurs left a crater 180 kilometers wide. It ended 75% of life on Earth, and we're still finding its dust in rock layers around the world. Under Antarctica, right now, there's a crater 2.5 times bigger, and nobody has ever touched it. That's not the strange part. The strange part is that it might line up with the worst day this planet has ever had. And it's one of at least 10 things buried under that ice that don't make sense yet. In 2006, a team at Ohio State, led by Ralph von Frese, was analyzing gravity data from NASA's GRACE satellites. They noticed something wrong with East Antarctica, a massive concentration of mass sitting inside a ring structure, roughly 500 kilometers across. The signature looked like an impact crater, a big one. The timing is what gets people. The estimated age places it right at the Permian-Triassic boundary, 250 million years ago. That's the Great Dying. 96% of marine species gone, 70% of land vertebrates gone. The worst extinction event in Earth's history, and we still aren't totally sure what caused it. The catch: the crater sits under 1.5 kilometers of ice. No one has drilled to it. No one has a physical sample. The evidence is gravitational, real, measurable, but indirect. And plate reconstructions place it directly opposite the Siberian Traps, one of the largest volcanic events ever recorded. Some researchers think a big enough impact can trigger volcanism on the opposite side of the planet. So either something hit the Earth hard enough to crack it open from both ends, or it's a coincidence. Either way, we can't check. The ice is in the way. 4 kilometers below the East Antarctic ice sheet, there's a lake the size of Ontario, Lake Vostok, sealed from the atmosphere for roughly 15 million years. Russian drilling reached the lake's surface in 2012 after decades of work. The accretion, ice, the refrozen lake water clinging to the bottom of the ice sheet, contained DNA from over 3,500 organisms, bacteria, fungi, sequences that matched fish. But one sample, pulled from 3,607 meters, contained something that made no sense. Hydrogenophilus thermoluteolus, a bacterium that, until that moment, had only ever been found in hot springs in Japan. It needs heat. It's thermophilic, and Lake Vostok is supposed to be near freezing. Two possibilities. Either this organism adapted over 15 million years of isolation into something that thrives in cold water, which would be wild, or there's a geothermal heat source at the bottom of that lake that we haven't mapped. The geological setting actually supports it. Helium-4 signatures in the ice suggest deep tectonic activity. We still don't know which one it is, and honestly, neither answer is comforting. In September 2025, a paper dropped in Nature Communications that quietly changed the map. Using 10 years of ESA Cryosat-2 radar data, researchers found 85 subglacial lakes that nobody knew existed. The total count of active lakes under Antarctica jumped to 231. But the word active is doing a lot of work here. These lakes aren't just sitting there, they drain and fill in real time, and they're connected. The team observed 5 lake networks where one lake drains and a downstream lake fills in response, like a pulse moving through a system. Antarctica has a hydraulic circulatory system under its ice. We've only just started mapping it, and we don't know what happens to it as the ice above gets thinner. Speaking of things under the ice that we probably should have found sooner, 138 volcanoes. Radar surveys added 91 previously unknown volcanic structures to the count, making West Antarctica one of the most volcanically dense regions on the planet. Most of them are dormant. But there's a feedback loop buried in this that doesn't get enough attention. The ice sheet is heavy, really heavy. It presses down on the magma chambers beneath it and suppresses eruptions. As the ice melts and that weight lifts, the pressure drops. Magma rises. Eruptions become more likely. More eruptions means more heat. More heat means more melting. More melting means less pressure. It's a self-reinforcing cycle. Slow. We're talking centuries, but already theoretically in motion. Simulations have run thousands of scenarios, and the direction is consistent. And this connects to something even older. In 2020, researchers from the Alfred Wegener Institute pulled a sediment core from near Pine Island Glacier and found a dense network of preserved roots, pollen, and spores. A temperate rainforest at the South Pole, 90 million years ago. Average annual temperatures about 12 degrees Celsius, which sounds modest until you remember there was no sunlight for 4 months of the year. To sustain those temperatures at that latitude, atmospheric CO2 would have needed to hit somewhere between 1,120 and 1,680 parts per million. That's up to 4 times current levels and roughly double what climate models had predicted was even possible for that period. So either the models are significantly wrong about how CO2 and temperature interact, or there was another warming mechanism we haven't identified yet. Neither answer is great. One means our models are wrong, the other means we're missing something big. And then there's the physics that just feels wrong. The rivers under Antarctica don't follow the landscape. The ice above is so heavy that it forces meltwater to flow against the slope of the bedrock, uphill toward zones of lower pressure. As the ice thins, scientists predict these rivers will jump their banks entirely and carve new paths. A river system running by different rules than anything on the surface. Near Mount Erebus, Antarctica's only active volcano, volcanic steam has hollowed out a cave system that reaches 25 degrees Celsius, warm enough for a t-shirt. Some of these caves have openings to the sky, natural skylights, and their own microbiomes. Plant DNA from moss and algae species that don't exist anywhere else on the continent has been found inside. These caves may have been refugia during ice ages, pockets where life survived while everything around them froze. And beneath the Wilkes ice stream in West Antarctica, scientists in 2022 used magnetotelluric imaging to find something else. A massive aquifer of ancient seawater, not meltwater, ocean water, trapped when Antarctica first froze over millions of years ago, water from an ocean that no longer exists. No one has sampled it yet. New radar mapping has revealed an entire pre-ice landscape buried under 2 kilometers of ice. Mountains, valleys, river basins, frozen in place for 34 million years, never exposed to weather, never eroded, geologically pristine. We're looking at the surface of Earth as it existed before anything resembling a human had ever walked on it. And in early 2025, researchers cross-referencing scattered pink granite boulders on the surface with deep radar data found something they weren't looking for. A granite body nearly 100 kilometers wide and 7 kilometers thick, sitting directly beneath Pine Island Glacier. Granite that formed 175 million years ago during the Jurassic. It doesn't match the surrounding volcanic rock. It shouldn't be there, and it might be influencing how one of Antarctica's most unstable glaciers melts, in ways that aren't in any current sea level model. We talk about Antarctica like it's empty, a white desert at the bottom of the map, but under that ice there's a crater from the worst extinction in history, a lake with bacteria that defies its own temperature, 231 connected lakes pulsing like a circulatory system, 138 volcanoes held down by the very ice that's melting, a fossilized jungle that breaks our climate models, rivers that ignore gravity, warm-lit caves with their own ecosystems, an ancient ocean sealed since the continent froze, a 34-million-year-old world preserved in perfect detail, and a 100-kilometer rock that geologists are still arguing about. We haven't even scratched the surface. Literally.
If this changed how you think about what's under our feet, subscribe. I'll see you in the next one.